3 o'clock here in the Netherlands, in Noordwijk, next to the sea. And I must say that today we are addressing one of the hottest topics in the story of photonics. We are talking about 3D printed optics for the tens of people in the Zoom room, the 120 companies who registered and gave input for the meeting today, and the thousands of people who are joining this meeting from YouTube, and they're going to watch now or later at any time. Before we start the meeting, I have to tell you one thing. I've been traveling again like crazy. I've been talking to many companies, many EPIC members. The scarcest material in our industry is not titanium, platinum, gold, or tungsten. The scarcest material in our industry is people, is talent. So I hope that all of you are either employees that are happy at their job or employers that provide a safe and happy place for people to work, because this is an employees market. If any of you is not happy with their position, find another job. This industry is desperate for having you. And I'm desperate to start the meeting today. Ladies and gentlemen, 3D printed optics. ASML is the biggest success story in Europe in equipment manufacturing for semiconductor production. If you want to see how they took the market away from Canon and Nikon, I recommend watching this video. But today, I want to tell you about what I believe will be the next success story in manufacturing equipment, and that is 3D printing of optics. Creativity is indeed the engine behind technological evolution. Wise words from FEMTOprint CEO Nicoletta Casanova. The trend in smart devices is smaller, cheaper, with an exponential increase in complexity. It's done by integrating fluidics, optics, mechanics, and electronics into a smaller volume. But there is a paradox. To produce small things, you need large, high-maintenance infrastructure. Up to 95% of the energy budget of a clean room is simply to control the air. That's incredible. Or maybe not. On Monday, November 15th, we address the booming field of 3D printed optics. And it really is booming now. Nanoscribe was acquired by C-Link, a pharmaceutical bioprinting company. Multiphoton Optics was acquired by Heidelberg Instruments in a smart move, having both additive and subtractive manufacturing for microprinting of optics under the same roof. Vanguard Photonics, thanks to the collaboration with Picontech and the Pixa pilot line, moved the technology forward for the packaging of photonic integrated circuits, and even newcomers such as the Italian Up Nano have attracted major interest. And when it comes to ophthalmic optics, another huge breakthrough happened in Europe in 2021. Dutch company LuxExcel started production of 3D printed prescription glasses. Today they are the only company in the world that can do this. But in the same way that ASML's success story was built around cooperation with strong partners, think about the twin scan, the immersion process, or the early move to extreme UV, these companies in 3D printing optics also need powerful partners to enable the next generation. And here are some of my thoughts. And in the two-photon polymerization process, there are two secret ingredients in the recipe: the polymer material and the femtosecond laser used for locally scribing the structures. Tunability of the pulse length and accurate beam shaping have been always items in their Santa Claus Christmas list. And for the 3D printed optics by LuxExcel, part of their success is because of the smart integration with electronics. Look at these electrochromic lenses turning your glasses into sunglasses instantly. Or the integration with augmented reality enabled optical waveguides, so you can have for the first time prescription glasses with augmented reality. Partners are essential for success, and when industry needs partnerships is when EPIC really is epic. Do you need faster turnaround time, regional production, or prototyping of optics or micro-optics? Do you want to propose your photonic technology as enabler of this success? Do you want to integrate your electronics or fluidics with the next generation optical elements? Or do you want to invest in the next big thing in manufacturing equipment? Do not forget to register online at the EPIC website. I'll be watching out for you on 15 November at 3 p.m. And it is 15 November at 3 p.m. You know, many people are asking me, are you acting? Do you really feel that excited about optics and micro-optics? I'm a really, really, really bad actor. I think I'm a better scientist than actor, and I no longer neither, but I'm a really bad actor. Do not hire me for a position at a movie company. Today, we are talking to 750 EPIC members for the next generation micro-optics, from equipment to manufacturing. Thank you very much, all of you. And what I do with all of you and the rest of the EPIC staff, 15 people. We welcome Elisenda, our new marketing manager, 15 people dedicating their life to this industry, is to know each of you individually. And many of you already know EPIC, organize events, provide access to your network, help you raise capital. We have the biggest website to find a job in Photonics, jobsinphotonics.com. And thanks to our market strategist, Tracy Vanek, we provide you with exclusive market data. Today we are at almost by the end already of season 5. Time flies. I can already tell you as a teaser, season 6 will be announced later on this week. But today we are talking about 3D printed optics. Have a special attention to the meeting on the 6th of December, medical device manufacturing in Europe. That's going to be fantastic. But also for those of you who are active in quantum technologies, on the 1st of December, we talk about large-scale qubit generation with Quantum and companies alike in the room. Do not miss that one. Today, I would like to first of all acknowledge the sponsorship of 2 sponsors today. First, coming all the way from Finland, Modulight. You're looking for a supplier of semiconductor lasers. Modulight provides growth, packaging, and all the way to provide final solution to the end users. A success story in Finland, in Europe. And second, SUS MicroOptics, all the way from Neuchâtel. They provide advanced micro-optics manufacturing, freeform optics at wafer scale. One of the success stories of the European micro-optics revolution. I would like to also acknowledge our cooperation, or strategic cooperation with UK Metamaterials Network. And last, but definitely not least, our media partner, Electro Optics. Thank you very much for promoting everything that we do at EPIC. Today, I'm going to be co-chairing this event with our expert in optics manufacturing, Dr. Panos Vergyris, and we have a fantastic agenda. Look at that agenda. Director, technologist, CEO, CSO, co-founder. We took to the companies at the highest possible level, because this meeting is about cooperation. These people come to the meeting to find potential cooperation with the rest of you. Today, 120 companies registered for this meeting, 120 companies. And Panos and I took the time to separate them into different parts of the supply chain. So we have the entire supply chain here: system integrators, equipment manufacturers, laser developers, process suppliers, materials. Everybody is here. Please make sure that on the next 2 hours, you scout at least 1 or 2 business leads. That will make this meeting helpful. And for those of you who are watching this meeting in YouTube, I have to say that if you want to get in touch with any of the participants today, all you have to do is send me an email, jose.pozo@epicdash.com, and I will make sure that you are formally introduced. And this is, of course, also valid for the people with me in the Zoom room. 120 companies registered for the meeting today. If you want to get in touch with any of them, please contact me and I will make the introduction. But most important, definitely most important, if you are here at the meeting, you are here at the meeting to find new friends. We have an internal chat. So use it, abuse it. I want to see you typing. I want you to get in touch with each other on the next 2 hours. We are here not only to find out about technology trends, but to answer the EPIC question. What can you do for the others and what can they do for you? And to start the meeting, I want to welcome to the room a new friend of mine. I talked to her already for a few months, because she wants to bring the entire industry together in the UK for the metamaterials manufacturing, and she's engaging end users. And I said to Anja, well, we had the same job. You have to come here, tell us what to do, and bring one of your end users to see what are their unmet needs. I welcome to the room for the first time in many times. When we talk about the metamaterials, it's going to be always with us, Anja Roeding, director of the UK Metamaterials Network, all the way from the UK. Anja, good afternoon. Tell us what you do and introduce the end user that came with you to talk about 3D printed optics.
Thank you very much for having us today. I am so delighted to be here. It's a huge pleasure. I just noticed that one of my technical speakers actually did not receive the invitation to this meeting. So I'm all on my own. Let's see how that goes. Right, let me share my screen with you just to introduce Metamaterials to you. There we go. Hold on. No. Oh, I'm so sorry. Technology issues in the background.
I'm sure you can manage.
Oh, it'll be all right. So, well, let's.
Bottom of the Zoom room, you have an arrow up says share screen, press it. I think you are in business already. Yes, perfect.
There we go. Okay, marvelous. So the UK Metamaterials Network is a very new initiative. We only started in March this year. And I don't know whether anyone of you is familiar with the concept of metamaterials yet. But metamaterials are basically structured materials that are technology enablers. So they are made from metals or plastics, and they derive their specific functionality to control waves, energy, and information through the way they're arranged, so their shape, their geometry, the size, orientation, their density. Why they are important, you may or may not be interested in these figures, and obviously, you know, with all market reports, take them with a pinch of salt. But the metamaterials market is due to increase massively in the next 5 years. So there is a huge opportunity here to utilize these technologies enablers to make, for example, antennas lighter, smaller, faster, to help with holographic displays to make materials very, very strong for use in harsh environments, to utilize metamaterials for noise control and high resolution imaging. So they have huge application potential. And we decided in the UK that we need to have a network that brings together academia and industry to really build the bridge to get the metamaterials out of the labs into the technology applications. So what we would like to do in this forum is really just raise awareness that metamaterials are out there. If you're not already aware of them, it probably may be an idea to talk to us or talk to metamaterials experts in your vicinity and understand how they may be able to help you with your scientific challenges. So let me just check very quickly if Kwong is here. Naringa, have you seen Kwong by any chance?
So Kwong is our technical expert of electro-optical systems at the MBDA, the market leader in missiles, and he's gonna join the meeting later because they have some challenges in their supply chain that they want to exchange with the rest of the supply chain. But before we do that, we introduce the topic. Today we are talking about micro-optics and larger optics manufacturing in 3D, and we have some of the top companies in the world that actually are in Europe with that topic. We want to find potential cooperations for them. So let's start. And to start, I want to go to the beautiful Karlsruhe. I want to go to Karlsruhe to meet the CEO and founder of the company. I already talked to them about them a lot. The company Nanoscribe. Let's meet Martin Hermatschweiler. Martin, thank you very much for being with us this beautiful afternoon. Congratulations on all the amazing business negotiations in the last months by Nanoscribe. I'm looking forward to June. You know why, Martin? Because on June we organize our epic meeting on advanced optics, and Nanoscribe finally present, everybody there. But first, we want to hear from you, Martin. The floor and the attention of everyone, today we are global, goes to you.
Thanks a lot, Jose, for having me. It's really a pleasure to be with you. So let me just give a brief introduction into Nanoscribe. Jose, you mentioned it before. Nanoscribe is now, meanwhile, a BICO company. We have been acquired in June of this year, belong to a group with more than 1,000 employees. Nanoscribe itself has about 80 employees. We invest a lot into research and development. We have more than 3,000 system operators outside, distributed over more than 30 countries. And meanwhile, we're in the 14th year of operation with many publications done with by our marvelous customers. So I invite you to have a look at our key enabling technology, two-photon polymerization. We have 2 white papers that go into the details thereof. Both of them are more than 20 pages long, so I will keep it short here, but I just want to make one point. Maybe something that is unique with our products is the ability to do two-photon grayscale lithography, not just two-photon polymerization, but two-photon grayscale lithography. And that's based on the fact that you can tune the laser focus and the size by increasing or decreasing the laser intensity in the laser focus. And if you do that electronically well controlled, you can do this on a 100 nanometer grid as we do it. And this results in the ability to form, for instance, a curved surface with just one slice. And this reduces the print time excessively, and it results in optically smooth surfaces. You can, for instance, get rid of concentric rings that you typically find when you, no matter how fine you slice an object, if you have a hemisphere in the center zone, which is the most important zone of a micro-optic, you will always find concentric rings. For two-photon grayscale lithography, you can completely get rid of it, and this results in baby smooth surfaces, so sub 10 nanometer surface. So there are 2 topics that I would like to talk about today. So mastering of micro-optics is of specific importance. It's not just 3D printed micro-optics, but also 2.5 dimensional surfaces. So the design freedom translates into superior performance because of high design freedom, like higher filling factor, sharp edges, smooth surfaces, and at the same time, you can also realize hybrid optics, so diffractive and refractive combined. And not only can you do this on wafer level, but you can also do it well aligned on fiber tips, on chips, or on the wafer. And because it's so easy to use, and in most cases, you do not even use spin coating and other complex processes, you can realize prototypes easily, iterate fast, and the few process steps involved result in high quality of your structures, high yield, and great performance. So I have brought 3 examples with me. So on the left side, you see such an arrangement of a hybrid optics. It's a hemisphere, and on top of it, you see fine ripples that diffract the light. Or you can even go beyond the economical compromise of diffractive optical elements, where you typically have only 8 diffractive optical element levels. In our case, due to the superior design freedom, you can go to more than 4,000 levels. This then results in quasi-continuous profiles. Or you can even implement a certain designer angle in order to get rid of the 0th order of diffraction. So diffractive optical elements which are blazed. And our process is also fully compatible with standard mass manufacturing processes. So if you think about mass fabrication of structures, you can either create a nickel shim, or you take a soft mold based from a polymer master, and then you do either injection molding or hot embossing, or you do nano imprint lithography. And as one exemplified structure, you see here an 8-inch wafer. This has been done in collaboration with EVG as collaboration partner. This is based on nano imprint replication. The second aspect is not just printing on wafer level, but printing optical devices at the point of destination for photonic packaging. And here Nanoscribe provides 2 major routes. One is to print optomechanical aligners so that you can easily click, for instance, a fiber optic to a certain mechanical alignment element, or you go the optical route and you print the optics at the edge of a chip or at the facet of a fiber or onto an optical chip at the top surface. This is how it looks like if you take our Quantum X system, the 2-photon polymerization maskless lithography system and 3D printer in one unit. And you can see in the camera directly where you want to print, and the alignment allows you to precisely anchor your structure with ± 100 nanometer precision to the point of destination. So no complex gluing, it's just printing at the point of destination. One example is from customers from the University of Münster, the Wolfram Pernice group. They, for instance, print things like complex taper structures in order to couple light into this waveguide. Then they have a total internal reflection that reflects the light out of plane, and then a focusing hemisphere with 8 micrometer radius, and that focuses the light into an optical fiber or vice versa. This is very broadband. It spans the complete visible range at low losses. Or you can print on fibers and fiber arrays. Here you see a V groove, and our system allows for automatic recognition of the fiber core, alignment, and printing thereof in order to print MicroOptics, which relax the mode field diameter. So to summarize, with Nanoscribe, you have the ability to two-photon polymerization additive microfabrication for MicroOptics, which results in superior performance, the ability to rapidly prototype, to do this in a robust and cost-saving manner, and it's also mass scalable by nano-imprint lithography and injection molding. And in photonic packaging, you can achieve good coupling efficiencies on surface and edges that relaxed alignment tolerances enabled by larger mode field diameters result in low losses and a high coupling reliability. And it's also versatile. Our products allow to print not just on wafers, but on fiber tips and on chips. And it's also very time-saving if you think about the alignment task and the gluing task that you can completely skip. So it's a very versatile technology, and if you wish to evaluate our technology, please just send us an email, inquire us for with your design ideas for feasibilities. Thank you very much.
Thank you very much, Martin, for a great presentation. I really have to say that I really look up to you and to your team for the amazing things that you are doing. Michael Thiel, you are watching. Hello, you are one of the people I look up to the most in this industry. It is amazing what you are doing. And I want to bring EPIC members in contact with you so it can help you doing even better. So you're prepared for this. The EPIC question: what are your new challenges? What can you do for the others, and what can the others do for you?
So what we can do for others is to do a feasibility study. So whenever you have something you would like to evaluate, please come to us. Do not hesitate. If you have specific photoresist, if you are a photoresist manufacturer, please consult us. We would love to test your materials. What we can do for you is we can print micro-optic masters for innovative replication techniques. So if you have anything that you would like to test, we print it for you and you can test the replication. Or if you want, we can print complex micro-optics to qualify maybe your measurement, your techniques that you have for metrology instrumentation, for instance.
We have many people in the room that I want you to meet, but I'm going to start up there. I'm going to start on the space market. We have one of the companies who's making a difference in the industry for the space technologies. We have in the room Leontios representing Leo Space Photonics. I wanted him to be here because in the previous meetings we'll talk about optics for FSO, for free space optical communication. And he's one of the key companies in the nanosatellite business, bringing that industry forward. Today, Leontios, we are talking about 3D printed optics. What is your interest in that particular topic, and what challenges do you have for your space applications?
Okay, so thanks, Jose, for giving me the opportunity. So basically for space, we are looking into, on our end, space transceivers for satellite optical communications. Either these are FSO or even inside the satellite. Now, the challenge here is to have, for space, you need to have very simple builds and very robust builds, modules. So the 3D printed optics, I think it is in the right direction because you can eliminate a lot of interfaces inside the module and make it more robust. At the same time, the challenge would be, and this is to be presented to the vendors here, the wide temperature operating range. So the modules are going to be cycled over -40 to +85 degrees C, for example. So the robustness of these 3D printed optics in such a wide range of temperature is one thing. And the other important thing is that for space, there's no air, and there's a lot of outgassing due to the vacuum environment. So the robustness against the vacuum operation is another thing to be considered in order to have at the end a space compatible or a process for making 3D printed optics for space photonics.
Martin, when it comes to space, for me, ideally was the first application that came to mind when I met your company 12 years ago. Oh my God, we are old. When I met your company the first time, then that was the first application I asked about. What is the current state of the art for 3D printed optics with two-photon polymerization in space applications?
Space applications, I think, is still a relatively new topic to two-photon polymerization, but there's a growing demand. That is what we sense. So space applications, also in terms of microfluidics, we sense a lot of requests to that. So the materials, since they do photopolymerize very efficiently, they do not outgas a lot. So therefore, I can imagine that even for space application, we can qualify two-photon polymerized optics for space.
We have a comment right now coming all the way from beautiful Vilnius, Lithuania. Leontios, listen to this. Mangirdas, thank you very much for being with us. What's on your mind? From Laser Research Center at Vilnius University.
You're asking me?
Yes.
Right? Yes. Okay, so there is a way how to make these 3D printed optics inorganic. And this makes them much more transparent, resilient, and resilient to everything, to high and low temperatures, to pressure variations, to acidic or whatever environment, also for mechanical effects. So just like glass, 3D printed at micro scale with all the possibilities to integrate or to print on chip, just like Martin has showed us. So the same devices can be converted from polymer to inorganic substance, glasses-like materials, as well as ceramics and even crystalline inorganics. So I think it's enhancing and specifically targeting these space applications. And of course, the method is compatible with all the 3D printing machines, as Martin already showed, so it's widespread.
Leontios, how can, for a question by Leontios, Mangildas, how can we access this inorganic freeform micro-optics? Is there a way that we can test this already for the nanosatellites work of Leo Space Photonics?
For the material, you should ask another participant who's online here. So Dr. Maria Farsari for FORF. So at least one example module material as a standard one works with it fine. But at the same time, it's not limited to only this specific material. If you want some tunable refractive index or whatsoever, so there is a space for research as well. So
these meetings are magical, Martin. We have Maria Farsari all the way from Greece, from FORF in the room. Maria, Professor
Hi.
Farsari, good afternoon. We are really excited now. They started meeting really strong today, Martin. How can we access these inorganic micro-optics to put them in space applications?
Okay, so this is not as straightforward as it sounds, because you cannot directly print inorganic materials, but there is a process through pyrolysis where you can take organic inorganic hybrids and you can print them and then make them inorganic via this process. So we have developed materials that burn very nicely. As it sounds paradox, but anyway. So Mangiudas has done some very nice work. I think you're showing it already on the screen on 3D printing of this micro-optical components.
I want to address this topic later, but what a way to start the meeting. Martin really wants to comment on this. Martin, what's on your mind?
I have two remarks. First of all, we have just launched a material in July this year together with the company Glasomer. It's a 2-photon polymerization material that has glass nanoparticles inside, and after a sinter process, you get pure fused silica. That's one thing. The other thing is you can also take polymers and apply by atomic layer deposition, for instance, thin coatings. And these thin coatings help to prevent degassing, outgassing of a structure, and also they can be made anti-reflective. So if you want to have high performance optics in space, I think atomic layer deposition might be interesting to look at.
We actually have in the room, this meeting is getting great. We have Dorothea Helmer coming from the company Glasomer. You're looking for fused silica 3D printed material. Glasomer is really the key company for you to address. Dorothea, you just were acknowledged by Martin. What do you do in this topic? And tell us what room for cooperation would you like to start today?
Yeah, I completely, thank you, Jose. I'm totally excited to be here. And I totally agree that polymers in space is not ideal. So glass is a really good material. And after the calcination process, you can be absolutely sure there will be nothing leaking out of the material. And like Martin said, we have a really great Explorer kit with Nanoscribe. So if you really want to print some nano optics on your Nanoscribe machine, then definitely you can buy the kit already at Nanoscribe. And at Glasomer, if you are interested, we also sell some more exploratory kits for larger prints. So if you have a regular printer, maybe you don't have a Nanoscribe and you want to print some optics on your regular printer, then you can contact us and we can definitely sell you a nice composite material that you can get a really high purity fused silica optics from.
And if you're looking for glass shaping at room temperature, Glasomer is the company that you have to talk to. And Dorothea, you're doing a fantastic job. I'm coming to you later, but Martin, we have a lot of questions for you. The first one is coming from one of our key consultants in the EPIC network. Yuval Ophir is helping a lot of companies in developing their supply chain. Yuval has a question for you, Martin. Yuval, what's on your mind? I don't think we can hear Yuval Ophir, so I'm gonna read his question. What are the highest refractive index materials that you offer today?
At the moment, it's 1.62. So we have well characterized these materials and provide all the N and K values throughout the visible and in the near infrared for all materials. So 1.62 is at the moment the limit, but that can be overcome in the future.
The next question in the room is coming from the company MBDA, Kwong Man. Thank you very much for being with us today. You are one of our end users. Tell us, what's on your mind? Kwong, I think you are muted. Yes.
Hi, sorry, I hope you can hear me.
The
question I had was what waveband your optics designed for? It sounds like you're working in the visible and the infrared. Can you go out to the mid-infrared and long-wave infrared?
Maybe Dorothea knows better how fused silica performs in the longer wavelength regime. I'd say that probably the polymers will not be good for the infrared, and but maybe Doro, you know better.
So around the 2.7 micron, where the OH group usually absorb a lot, we have very low values because we do vacuum sintering, so we don't have a lot of OH groups left there. So, and in the longer UV, it's the same as regular longer infrared. It's like the same as the regular fused silica glass. So, at some point in the UV, you have a cutoff, and at some point in the IR, you will also have a cutoff, definitely.
The next question in the room, more than a question, is perhaps a challenge or room for cooperation, is coming all the way from the United States of America, and this company is Nanobox. A person who's meant a lot to the online technology meetings is James Field. James, good morning for you, good afternoon for me. What's on your mind?
Good morning, Jose. We're well caffeinated here in the Northwest. One of the questions I have is we're trying to scale our high and low index monomers for gradient refractive index printing. They have to be inkjettable, but we're trying to get out of the small batch mode. So we're looking for partners to help us scale our production as we get to volume levels. We have a customer that needs to make 24 million optics in a year. And to do that, we have to have those materials scale. So anyone who is interested in talking to us about scaling our monomers, please call.
So you're
Please
looking for a partner to scale your monomers. We are talking about high and low refractive index monomers
Correct. Yes.
for 3D inkjet printing.
Well, yes. So they have to have the viscosity to inkjet print. Also, they have to work together well because we blend them during the printing, and we add nanocomposites to sculpt the light through the monomer. I want to say that we've been LEO qualified, so we've gone through radiation testing, and we are doing some optics for NASA in both mid and long wave IR. So we have some different skill sets across the pond, but we hope to collaborate with Europe in the future.
You have to get in touch with Leo Space Photonics, by the way, James. I think there has to be a nice meeting there. And I want to have the final question for you. Martin is coming from NTU. We go to Matthias Parrot. Matthias, thank you very much for being with us today. What's on your mind?
So hello, everyone. So I was wondering about the smallest voxel volume achievable by Nanoscribe printers using 2-photon polymerization, and also the smallest thickness of a stealth standing wall achievable.
Yeah, a great question. So the smallest features typically go down to about 100 nanometers. And then, of course, things get tricky. So mechanical stability becomes then an issue. And if you think about some wall that should be minimum in size, but it should also not fall over, so mechanically still stable, then often a lot of tricks are involved, like supercritical point drying in order to keep it stable. And if you think about replicating some geometry by injection molding or by nanoimprint lithography, then often it's not the 2-photon polymerization mechanism that limits the performance, but it's mostly the injection and nanoimprint methods that are the limit. So roughly said, 100 nanometer smallest features, and let's say the mechanical robustness depends a lot on the geometry itself. So one has to look at it at the case individually.
Thank you.
Matthias, let's look at your case. This is a business meeting. You come all the way from NTU. This is the Nanyang Technology University in Singapore. I visited the university myself. Why did you ask that very good question? I agree with Martin. What challenge, what application are you targeting?
Well, there is obvious applications in so especially in conjugation with this technology of so offered by Glassomer now, but which was basically studied in the 2017 paper by Kotz in Nature, but I'm pretty sure a lot of people here read but kind of brought. I mean, to me, it was like a shock, like, oh, this thing is possible, and so I had a lot of interest in printing guided optics using this technology. So that's why I'm interested in all these printers and these new resins, which hopefully are good optically and good enough for printed optical circuits and other guided optics. So it's a really interesting topic.
I'm very impressed with the activities that NTU is doing in silicon photonics, in biosensing. I visited your lab myself. I didn't see any 2-photon polymerization machine there. Is there? Let's change that today. Yeah, let's do that today after this meeting. Let's continue this fantastic meeting. We go from Nanoscribe to a person, to a company and a person that mean a lot to EPIC. We go to the company FEMTOprint, and we're going to meet Andrea Lovera, the Chief Scientific Officer of FEMTOprint. They joined this meeting with certain challenges for the supply chain. After the presentation, I want to go to MBDA, understand the reason why they're at this meeting, and try to make some connections within the members. So before Andrea Lovera, Chief Science Officer of FEMTOprint, the floor and the attention of everyone comes to you.
Thank you very much, Jose, for the invitation and for the introduction. So I'm going to talk about glass, which is a nice transition compared to the discussion we just had. So we were talking about printers, glass optics, and this is actually what we can offer. So a few words about the company FEMTOprint. We are a Swiss-based company. It's a small company today, but nicely growing. We are about 30 people, and we sell all around the world micro devices printed out of glass for many different markets, from life science to automotive, aerospace, watch industry, and of course, optics. Our technology is actually the opposite of what we have just heard. So we are not really growing material, but on the other side, we are removing material from a substrate. And the fabrication is done using a two-step process. First of all, we expose the material with our laser machines to inscribe an image of the object we want to fabricate, like in the left. And then we go into a chemical etching solution that selectively dissolves the material that we have exposed. And in this way, because we exploit only the voxel to modify the material, we can build things that cannot be produced with standard, for example, lithography or fabrication technologies, like this connector, which has a channel which are buried into the volume. Our main material for optics is fused silica, and there are many advantages for using fused silica in the optics because it's, for example, UV transparent, and there is transparency windows which goes very nicely to the IR. It's stable, can go to very harsh environment, is biocompatible, therefore elements can also go into a human body or being used in lab on chip, for example. And the fabrication can be, of course, done at wafer level scale. Here we see an 8-inch wafer. These are just holes, but in the same area and surface, we can basically produce any type of components. And what is also, I think, amazing of what we do is that we can achieve very, very thick parts. Here, we can reach 20 millimeter in thickness. Aside of the main technology, we have built in the time many other post-processing that helps us in tackle different markets, like a surface polishing method that allows us to really reach the optical market by decreasing while improving the surface quality of the produced components. Then we have encapsulation technologies. We can modify the refractive index of the materials, drill holes. And more recently, we are also handling metals to create electrodes in 3 dimensions and other type of functionalization through partners. This is an example of a glass components that we have produced for CILETI in Grenoble. It's a complex monolithic fabricated piece that includes out of plane lenses in the center and then freeform mirror on the side. The whole idea was to build a particulate matter sensor, but integrated with pre-treatment optical imaging in the device. Then other possibilities that can be offered by the technology, of course, are true freeform fabrication. And this is another example of commercial part that can be purchased from Thorlab website that we have tried to reproduce with our machine. And without going into the detail, here on the left, we see an image of the parts produced with the laser and etching that, of course, needs some post-processing to decrease the surface roughness. And on the right, the same shape after surface roughness smoothing with our process. So because I knew that you were going to ask the question, what can you do for us? I think we are really looking from the market. We are really looking for partners to bring ideas and devices at the table to develop together with us. And what we can bring here is our expertise in producing from micrometer to several millimeter size component. We are really comfortable now to work with typical feature size in between 20 micron and 1 millimeter. We can decrease the surface roughness below lambda 10, average roughness below 20 nanometer. We can keep a shape accuracy below 1.5 micrometer compared to the 3D model. And we are comfortable in producing curved shape for the moment using our localized polishing process. And what we really hope at the end of this meeting, but also for the future, is to really find good partners and customer to co-develop know-how and new products. And what can we do for you? Well, we offer a flexible 3D technology, which really allows us to operate in different markets. And our main offer today can go from fabrication of master. I think we heard a lot about master in the previous presentation. We have demonstrated with few selected customers that also our technology is compatible with replication for injection molding machines and other technologies. But in the same time, we can offer fast prototyping, small volume production, till to mid volume production of optical components and other. And with this, I'd like to thank you for your attention.
Thank you very much for a great presentation. I'm still puzzled about when to use glass and when to use polymer. To be honest, there is so many industry trends that it's hard for me to summarize that in a sentence. I don't think there is a clear sentence for that. Luckily, we have lots of different end users with different challenges when it comes to what material to use. So I want to bring to the attention a few end users that we have in the room. I'm going to go first to MBDA. Kwong, Man, good afternoon, all the way from the UK. MBDA is a company in the defense sector. We all know the company MBDA, and you know what is your business. What is your interest in 3D printed optics? And when do you target polymer or plastic? And when do you target glass as the material to do those optics?
Hi.
And if you have any slides to share with us, now it is also a good time.
Yes, I'm just gonna share that. I've only got a single slide, but hopefully you should be able to see that right now. Can you see that?
Let's see. Yes, you go slideshow mode.
Excellent. Okay, that's brilliant. So MBDA's interest in metamaterials. We've only started engaging with you guys with metamaterials recently, but so brief description. MBDA is a European complex weapon prime. So it is. My name's Kwong Man, and I'm the EO sensors technical expert in MBDA. So MBDA is the primary missiles company in Europe. So we use imaging infrared technology predominantly in missile seekers, but also we're interested in the technology for signature control. As we develop systems for the future, the requirement for our systems become more demanding and requires increased design flexibility. This could be to fit into smaller spaces where the overall size of the missile is reduced, or to fit into unconventional spaces, as in the case of multi-mode seekers. So metamaterials can help us deliver this challenge, where metamaterials have the potential to reduce the number of lens elements and operate in confined spaces. A meta lens has a sub-wavelength meta surface pattern manufactured on the optical substrate to convert a optical input wavefront into a desired optical wavefront by manipulating the scattered phase across the surface of the component. Some of this you've seen on the previous talks. So it sounds like there's some good collaboration there that could be possible. Missile domes can also introduce significant aberrations into the image forming beam, and it is possible to correct for this using asymmetric conformal surfaces. A metalens optical component could achieve optical compensation for imaging through conformal surfaces with more cost effectiveness than typical conventional freeform optical designs. The other feature, which I'm more interested in for myself, is the survivability. So there's the need for our systems to operate in more difficult environments where the systems need to become less detectable or more resilient to the adversary's capability to increase the survivability of our systems. Metamaterials could be used to control the material's emissivity, reflectivity, and absorptivity using technologies such as the graph we've seen as nanoresonators. So most infrared images operate in specific main wavebands due to the attenuation of our atmosphere. These include shortwave IR, medium wave IR, and long-wave IR. So metamaterials could be designed to promote and limit emissions of light in defined wavebands, and if these can be designed to emit outside the wavebands of detection and to reduce emissions within the wavebands of detection, this increases our chances of survivability. Another avenue is the directed energy weapons that can be used against our systems, such as laser dew or high RF energy. using metamaterials, you could design these features so that you can reflect the wavebands of interest, and again increase our survivability. Another factor is so other forms of detection use reflected energies to detect our systems, such as radar. Again, metamaterials could be used to specifically absorb these wavebands, so again reducing their return signal and increasing survivability. There are fields that, so these are the fields that the EO Sensors department imagine that metamaterials can provide some benefit for the future. There may be other areas that metamaterials could be applied in other technologies and departments. If you have any thoughts about this or any questions, you can contact me directly. That's all I had for now. If you have any other questions, please let me know.
Well, you have a lot. I love when an end user comes to the meeting with a particular challenge. So MBDA wants to start strategic cooperations in a step change in IR seeker design, step change optics, meta surface lenses. This is a very hot topic in the industry right now. We already saw the success stories that are coming out from every corner. I know that Neil Technologies is listening to this meeting. Who can help? Let me see. I have some hands up. James Field from Nanobox. How can you help?
Well, we've made imagers for missiles where we've printed right on the image sensor itself. That was field trialed, going through shock and vibration, the heat, humidity. So that they're used in the services or beginning to be used in the services over here. And we do control permittivity and permittivity of material sets for cloaking radar images and the like. So I will send you some presentations, Kwong.
Please, that'd be great. Thank you.
I want to also have a look at this slide. I will share it with everyone. Have a look at this meta surface lens. I think many of you are already telling me that they want to help, but they don't want to talk publicly. So I think it is okay that that we leave this as introductions offline. I know that the topic is the topic is the defense, and it's better to have the introduction and discussions offline. So don't worry, I know many of you want to help. Let's do the introductions later. I want to comment, I want to bring to the discussion, because we have a person from the automotive sector. We have Lionel Guillot. He told me it is too early to speak about my challenges. So I just want, because this is, of course, this is a meeting, not a webinar. I want Lionel to say hello to us, and I want to ask him what brought him to this meeting. Lionel Guillot representing the company, automotive company Renault. Lionel, good afternoon.
Hello, good afternoon. Thank you for giving the micro. Just to say, this is an early participation today. My interest is for functional surfaces, whether it's for optical aspects or photocatalytic aspect, and any aspect that we could imagine in a car for functional surfaces. So today I'm learning, I'm listening and learning to you, and that's very interesting. And I thank you a lot for these speeches.
Thank you very much, Lionel, for that. I'm sorry that I brought you to the room like this, but I think it's very important people get to know you. And I want to talk to you maybe later today or in another meeting about how the automotive industry sees the glass versus polymer. I've been told that this requires a separate meeting, and we are trying to arrange it. Lionel, thank you very much for that. We have some questions in the room for the company FEMTOprint. Dorothea from Glassomer, what's on your mind?
Yes, hi, thanks for the very nice presentation. I really love the FEMTOprint images. It makes glass look so nice. So I was wondering, you have this great technology of smoothing out, so which looks really good. So you, as I remember, make also channels on the inside of glass. Can you also smoothen on the inside, or is that a smoothing exclusively on the outside of the glass, basically?
No, unfortunately, we cannot smooth on the inside. We can only smooth on the outside.
And then what did you say the roughness parameters were roughly when they're unsmoothened?
So unsmoothened surfaces can be, in the best case, 80 nanometer, which is happening on the vertical sidewall, and on the 3D shapes in general, we are around 200, 250 nanometers.
Okay, and I have another quick question, if I may. So how fast for this really nice complex device that you showed? So how long does it really take to make such a a channel or a structure like that?
So for a part like that, the typical time is maybe half an hour to 1 hour, something like that.
And that's all on wafer scale. So you have thousands of them at the same time.
Well, maybe not 1,000 of those, but a lot. Yeah, we can fill the wafer.
Okay, and that's with smoothing. So half an hour, the whole thing is, laser on, etching, smoothing, everything.
No, that's the laser part. Then the etching is a parallel, and even if it's a bit longer, it doesn't matter because all the devices go to the etching one by one, while the laser processing is serial, so we produce one after the other.
Okay, cool. Thank you very much. Really impressive.
Yeah, it is really impressive, but also very impressive what Dorothea is doing. I'm a huge fan of Glasomer. It's so great to have you here. But we have another question in the room, but this question is for MBDA and is coming from NTS Optel in Nijmegen in the Netherlands. Frank Ernst, you're a system integrator and tester of optical instruments. What's on your mind? What question and suggestion do you have for MBDA?
Actually, I have more a question. We are building machines for the mass production of these meta structures. So, do you need those? Yes or no? So, I in the chat set the link. So this is maybe more a question to everybody. If you need these, I think we are market leader of these testers for mass production.
We're talking about optical testers for mass production. Of course, then the question was not for MBDA, who is mass production. Luckily, it is not in the missile sector yet, but there are many others. So let's discuss it offline with anybody who has suggestions on the testing. I'm going to look at all the optics manufacturers today. We have so many. So FEMTOprint,
exactly.
Nanoscribe, AMS, Synoptech, all of you, Chroma, SUS MicroOptics, please make sure that you tell us later. Maybe I will make a round Q&A later on your needs for testing. So Wilfred Null from SUS MicroOptics, stay alert to answering that question later. We have another question in the room. Is coming from my very good friend and top consultant in the industry, Ruth Huberts from ThinkMate Engineering and Consulting, and a person that we all know and love in the MicroOptics community. Ruth, what's on your mind?
Actually, I do not know what kind of question I just posed. I just gave you an information.
Yeah. So you told me that you are you just gave an invited talk at Wetzlar Herbsttagung this year, and
Which
you talk about the
with
glass or plastics.
Right.
Could you give us your first insights? How is the when it comes to micro-optics, how is the market looking at glass versus plastics?
Yeah, so when it comes to very small optics, typically plastics are the better choice. So you have many high performance plastic materials. I would not call them plastic because it sounds a little bit, but the question was actually glass or plastic. So whatever is below 500 micron could be a challenge for glasses. But I also mentioned Glasomer, which have basically a formulation of glass particles in polymer matrix, but you need high temperature processes for them in order to remove the organics, right? So that you get the performance of the material. And I haven't seen actually not good enough data. So I'm looking forward to receive some data of them to take that into account also for many customers asking me for advice. Thank you so much.
Thank you very much, Ruth. Ruth and I went last week to the PEAK International Conference, where we also met other people that are in the room, and we are very happy to see how two-photon polymerization is making a room in the packaging of photonic integrated circuits, a topic that I want to discuss after the next presentation. Before that, SUS MicroOptics, Wilfred Null, you have something to share with us.
Yes, thank you, Jose, for giving me the floor. Well, we look, of course, at all different materials, and the difficulty with glass is always, and Ruth just said it, it's the high temperature. That's one problem, and the other is is the high shrinkage, which makes it actually very difficult to get the shape right. So it really depends on the application. If you go to imaging optics, you need the perfect aspheric shape, and to get this right, polymers are still much more suitable in micro-optics, at least, than glasses. Glasses shrink so much that they deform so much that it's very difficult to compensate these forms in the masters. And the mastering process, the origination process is a very expensive process, as we all know. So that's why people opt for plastics. And so that's why what things that FEMTOprint do are great, because it's directly in the right material. So this is where their strength is, obviously.
And we also have to talk about the functionalization of the material, which is far more mature in glass than in polymer. But before that, Dorothea, you have something to share with us as well.
Yes, I just, what's a high shrinkage factor? And then again, if you have an isotropic shrinkage, then it really is not that big of a problem. So what's high for you when you say it's a high shrinkage
above
factor?
5% is already high.
Okay,
5 to 7% is high for us. So we
but
look at
like
materials that have much lower shrinkage factors than way below 5%. Actually.
Okay, but even if you do laser sintering of metals, you end up having 6, 7, 8, 9% of shrinkage.
And it's,
so
I'm not saying it's impossible. It's just very difficult to compensate. So this is, and there are definitely applications for these glasomers. I'm not saying it's not working, but we do imaging optics, micro lenses way below 1 millimeter, 0.5 millimeter in size, and they still have to be perfect aspheres with very low RMS deviations. And I haven't seen these glasses. It takes a lot of iterations until you get there. I'm not saying that it doesn't work. It's just much more difficult to get it under control.
Yeah,
even with plastics,
I know it works, so
I can tell you, even with polymers with low shrinkage factors, it still takes 3 to 4 iterations until you get the right lens shape, and this is a very expensive and lengthy process. So,
definitely. I mean, we do injection molding, so it's a question also of the design. It's not only a question of the material, definitely, but isotropic shrinkage, so you can really know what the part will look like in the end.
Okay, thank you. Well, we should talk again.
You have to talk. You have to know that both of you are really successful stories, so you have to find room for cooperation. Do it for me. Do it for me. Work together for me. I want to continue with the program. I already talked about the photonic integrated circuit packaging. Nanoscribe is pushing this to the limit. Vanguard Photonics pushing this to the limit. Multiphoton optics pushing this to the limit. You guys are doing an amazing job. I want to understand where this market is going. And this is one of the key applications of our next speaker today. We are going to a beautiful city. We're going to Karlsruhe to meet Philipp Dietrich, the co-founder of Vanguard Automation. Philipp, good afternoon. I think Karlsruhe is a fantastic city. I can't wait to visit it. The floor and the attention of everyone goes to you.
Yeah, thank you, Jose, for
slideshow mode, so we can see the quality that you deserve.
Yes, of course. I'm going in show mode. Yes. Now I'm in show mode. Thanks for the kind introduction and all the energy you bring to this meeting. This is much appreciated. All right, I'm talking about 3D lithography for photonic integration, and there's a big focus on photonic integration. We're not a 3D printing company. We're using 3D printers to do photonic integration. That's what's special about this. So what's our key challenge? We're looking into solve the following challenge. We're having 2 components. The prototype system is a semiconductor laser and a SOI chip, and we want to interconnect them. And what would you do usually? You would use active alignment, and that obviously works nice in some situation, but it's a very tedious, time-consuming, and less expensive process. I mean, it takes up for the majority of all costs of assembly. That's like if you build a car and you spend all the effort just on assembling the parts together. And we want to solve this challenge. We're solving it by the following process. We 3D print a freeform waveguide between optical components. You can see that here in green. We call this photonic wire bond. And the photonic wire bond can compensate misalignment of the chips. So if you're using a high-speed die bond, like you know from electronics, may has 10, 20 micrometer accuracy. So you have a misalignment of say 20 micrometer, our photonic wire bond can compensate this. So you have a simple task to assemble the chips. You can do this really fast, and we're then solving the assembly challenge by 3D printing something to it, and at the same time matching the mode field and doing all the rest. And a subsequent step, we're cladding these interfaces with a low index polymer. That's first of all for single mode operation. All we do is in single mode operation. And secondly, to be reliable, to pass Tilcordia tests and so on. I'm going to talk about this in the end again. I'm going to come back to this. So how does it work? At the, let's say it's the engine of our process, but it's just a small part. It's just a part, let's say it that way. It's a 3D printing process. It's also two-photon polymerization. So what we do, we take an objective lens up here, and we have a femtosecond laser beam that can focus into resist and polymerize it. And with this objective lens, we look at our laser, we look at our chip, we localize it with sub-100 nanometer accuracy. We automatically calculate the trajectory that connects these two chips, and then the machine does everything else itself. And that can go in quite attractive cycling times for many applications. And we supply the whole process. We don't give you a 3D printer. We sell you a process that connects optical chips. Just to give you an example, on the left side, you can see that here in green is a photonic wire bond connecting SOI chip here on the top with a laser. So this is 20 micrometers, so it's maybe 250 micrometers long. And you can see, if you look carefully, it's compensating some lateral misalignment, which would otherwise lead to, well, incredible high coupling loss. And we can do, with this, we can do typically, let's say 2 dB, that's a very reasonable value. We can go lower in some situations. So the performance is really attractive, I believe. Of course, our technology can be also applied to any other optical component, like a PLC photonic chip here that is connected to a single mode fiber. And if you look at the chip here, at the single mode fiber, you see a taper structure. The photonic wire bond is getting bigger. You can have nice mode matching to pretty much anything, and that gives you very low coupling loss. Now, with that said, we cannot only print photonic wire bonds, of course. We can print 3D lenses, for example. You can see them here. And our main value proposition is they're reliability tested. So I'm absolutely a polymer person in this polymer glass discussion. That is because we can make polymers reliable. And they have the key advantage that if you print them onto something, they don't shrink. Like we can have Tilcordia tests and have shrinkage well below 1%, like 0.5%. So it's really, really accurate. We can have plus minus 50, 100 nanometer surface accuracy. We can have sub 10 nanometer surface roughness. So the performance is really superior and at the same time very stable. Even for space application, we're close to NADA specs, to NADA output gassing specs. Now this is our key product. That's the Sonata. That's a 3D printing machine. It can handle big wafers, 12-inch, and it's a fully automated system. But that's not the only thing that we sell. We actually sell the whole package. So we also have a system which takes over the dispensing, the development, and the cladding of the photonic wire bonds. So this device is called the reprise, and this allows you to actually insert chips, sample chips, of course. We do the 3D printing, we do the resist dispensing, we do the development, we do the cladding. We go through, we give you the whole process. You do not need to establish the process of 3D printing the optical elements. We give that to you. So you can start fabrication with our devices. And just to give you an idea how the final interface can look like, here you have a single mode fiber array on the bottom left. It is a PLC chip. The machine does a cladding. You can see that here, and it automatically encapsulates everything and makes sure your devices are reliable. So to sum up, our product is an assembly line, or is a combination of machines, processes, material, software, everything you need to connect optical chips. We have typical performance of, say, dB. We have minus 30 dB radical reflection. That's important for lasers. And we have tested many devices for 85. We have tested them for minus 40, 80, typical 85, actually, typical telcordia specs. Actually, lenses have gone through high acceleration, reflow soldering, gold soldering, and so on, cryo operation, and even high power operation. So now to actually answer the most important question of this talk is what we offer is laser chip single mode fiber integration without active alignment. So solving a huge challenge, I believe. What we're looking for, obviously, customers that are willing to adapt our technology. We are demanding on rethinking your fabrication process, but I think we can solve very, very important challenge of photonic integration.
Thank you so much for that presentation. I have to ask you because we've been talking to you and to Christian Kos already for many years about how to bring the photonic integrated circuit community to interact with. I know that the collaboration with FICON-Tech and your introduction in the Pixar Pyro lane have made a difference. What is the current scenario? What is how do you define the technology readiness level for packaging photonic integrated circuits with two-photon polymerization?
Yeah. So what we can have is we have demonstrator assemblies, reference assemblies that show how the technology works. So that's that also has undergone telcordia tests, and that's a typical TRL6 level. So that's the level until we qualify products. Of course, customers that already have our machines are going further on this. So we've given them the process, and they're implementing it into their product, their building system of this, and this is then moving away from 6. But 6 is like I think that's a tested or a prototype in the relevant environment. So that's what we can give you.
I bring to the debate Martin from Nanoscribe and Willy from Multiphoton Optics. What is the current scenario? Is this a technology for prototyping, or do we believe that we can go into production for the packaging and fiber to chip assembly of photonic integrated circuits? Let's start, since you're the three of you very polite, let's start with Martin from Nanoscribe.
Clear, we go for production. That's the clear target. There's no excuse. It will go forward until mass production of optics. I'm pretty certain.
For many of the applications in silicon photonics, for example, the transceiver, the Rockley photonics in wearables, or even the technology for free space communication in nanosatellites, we are targeting large volume manufacturing. We are talking about millions per year. Is that a volume that we can target with two-photon polymerization?
Yes.
Yes.
Definitely.
Yes.
It's the fastest. Let's say if you think about the technologies on the market in 3D printing, in additive microfabrication, if you take the volume pixel, the smallest building block into account, then two-photon polymerization is the fastest technology on the market. And integrated photonics is a perfect example where both the shape accuracy as well as the volume are ideal for two-photon polymerization. It's inevitable that it needs to succeed.
I am as positive as you. I'm asking the questions because I want to hear what you're saying. Willy from Multiphoton Optics, don't be too quiet. By the way, Willy, I'm a huge fan of you as a person for how fantastic you are in what you do, but also big fan of Multiphoton Optics. How do you see this photonic integrated circuit packaging? This is still the eternal promise or the reality for this technology?
Yeah, thank you. So that is a very interesting topic. And it is a target for us to bring this to the production. So right now it is not really at a production level, but we are hoping to get this done pretty soon.
We have, sorry, I think Ruth wanted to comment. Ruth Hubers from ThinkMate.
Hi, I think both are right, but I think they miss one really major point is that you need to integrate that in a whole sphere of different technologies. So what we demonstrated, like in 2007 or so, before I founded this company, was that this is possible. And we had like a rate which was like 12 centimeter waveguides and a huge data transfer rate. But still, you need to implement that into a real environment, meaning each customer has a certain design and each customer wants to have something different, meaning the flexibility of the tool of the, let's say, 2-photon lithography is tremendous, but you need to adapt that and you need to implement that into the mass process. And I never would have founded multiphoton at that time when I would not have been sure that this is possible. And I still think you just need to do the right things. So it's up to the guys to do the right things.
I also bring to the discussion Henrik Gagson, which is also the founder of UpNano, a newcomer in this industry. Thank you very much, Henrik, for being with us today. You have seen the initial discussions. We talk already about glass versus polymer. We talk about 3D printing being only not for polymer. That was the first crashing argument that we had today. How do you see this industry, and what is the piece in the puzzle that you cover? And for the others, there's a couple of questions in the room. I'm going to come afterwards. Henrik.
Sure. So thank you very much for the questions. First, I'm not a founder of UpNano. I worked with Martin just until last year. So, but yes, I see absolutely, as previously said, the smaller the lenses, the more the polymer comes into its play. I would say absolutely. So, of course, I'm a polymer guy. Just as we've been talking about earlier on, 2-photon polymerization is an excellent tool for polymer optics. And of course, UpNano, the difference to the previous speakers is that UpNano makes a high-speed 2-photon polymerization printer, for example, for doing meta lenses and so on. I will just show you today's single slide.
Please show us. And I'm very, very, very amazed on how fast UpNano has made the machines already available for manufacturing. Please tell us, Henrik.
Exactly. So, of course, we work with glass, we work with glassomer, we work with polymer, and not only the non-fluorescent transparent material with high and low refractive index and so on. But what I want to show today, just quickly, is the equally important aspect, which is the possibility to block light, right? So we have the glass material, we have the polymer material, but we also see a great request for being able to block material. So in this case, we printed a polymer lens with a lens barrel, 1.4 millimeter in diameter. And of course, this can be holders for large meta lenses and can use in other way. Just wanted to introduce just quickly while we're here. And this material is super, super black. It blocks light from 100 micron thickness, basically.
Super black. And I want to come back to you later, but now we have to address a few questions that we have in the room. Yeah. The first one is coming from Switzerland, a MicroOptics manufacturer who has been introducing MicroOptics into instrumentation. Of course, I'm talking about FISFA. Guido Bonatti, thank you very much for being with us today. Tell us what's on your mind. I think you have a question for Vanguard and also for Multiphoton.
Well, my question was a very simple one. So as to my knowledge, most of this photonic wire bonding is used in telecommunication. If you would bring this up a level in power, can you tell me, is there a limitation you know by today for polymer, or I think Multiphoton is even working on OMUCERs, how far you can drive the power up by still keeping some lifetime?
Yeah, so we have tested that actually. We've used fiber to fiber connection as a simple test system, because there you can increase the power to a sufficient level to actually see failure. And the power levels to which we can go reliably is -27 dBm. If you go higher, you see some thermal effects, you see some heating, which causes deformation or whatever, and eventually actually also failure. For lenses, it's a bit higher. It goes in the 30 dBm region. but it's quite similar. I'm both talking about C-band. O-band we haven't tested, but it should be a bit better because absorption is low there. And now transferring this to the diode lasers, we haven't tested these power levels on diode lasers yet, but I would expect that we can easily go into the same region. The reason is we wouldn't 3D print the lenses directly on the facet because they have incredibly high intensities, but we would offset them by pillars. And then you have the beam expanded a bit, then intensity is not that high, and I think you can go into such power levels. Eventually that must be tested. So if you want approaches, we can have there an evaluation project. I have a suggestion for a suitable test system, and we can demonstrate that this works.
Panagiotis, Dr. Panagiotis Vergyris, you did a fantastic job bringing all these companies who are competitors, but at the same time, amazing friends. I really want to organize a meeting somewhere, maybe in Jena or somewhere like that, in a Switzerland of optics, and talk about polymer versus glass, because that will be, you know, and we're going to get t-shirts. I'm a polymer guy, I'm a glass guy. Panagiotis, you brought all these companies. I want to understand how they compare to each other. I understand there is one company who didn't show their one slide yet to bring the whole puzzle together.
Yes, it's true, Jose. This is amazing today what is happening. We have a lot of speakers covering all the supply chain, and we have a lot of participants, and I'm very happy for that. And it's true that Multiphoton Optics, Willy, would like to present also something to the rest of the participants. So please, Willy, if you want.
Okay, thank you, I will. Okay, hope you can see my slide. So I'm Willy from Multiphoton Optics. And we are developing a two-photon polymerization equipment. And with this, you can structure lens stacks, you can structure devices, you can structure lenses on devices and waveguides, diffractive optical elements, and so on. And most of the time, we use the industrially reliable material class of Hermatschweiler. And the applications are in the structuring of functional components and in mastering. And there are many mastering applications out there. And for example, you have here a picture of an electroplated replication tool. There we have some pyramidal structures replicated in a very huge area. Going back to the functional components, so the material class of Hermatschweiler has a very high optical resistivity, making them ideal for functional components. This test is a micro lens fabricated on a DFB laser, and the optical power was at a megawatt per square centimeter. And since now they are running for over 2 years and looks quite good, but they will run on and on. And the scalability of this technique is the resolution down to 100 nanometer. So on the right side, you see a metal lens, and this consists of different pillar sizes down to 100 nanometer and up to 450 nanometer. And also the scan speed. So we showed up to 1000 millimeters per second, which you can see on the bottom right picture. And the structures are up to a millimeter times a millimeter times a millimeter. So what are the questions? What can we do for you? We provide an equipment and processes for advanced 3D microfabrication. And since we are a part of Heidelberg Instruments, we have more technologies available, like maskless UV lithography or like thermoscanning probe lithography machines. And what can you do for us? You can get us involved at an early stage in your technology roadmap. That would be really great. And I'm thanking you for the possibility to talk to you.
Willy, what you have done and what Ruth Hubers has done in the previous years and the acquisition by Heidelberg Instruments are a success. Beautiful story in EPIC. Thank you very much for that. And I also would like to understand a bit what kind of partners and what strategic partnerships would you be looking for from this network? In essence, the EPIC question, what can you do for them? What can they do for you?
So, like I said,
don't repeat what is written. Give us a bit more meat there. Are you looking for any material suppliers? Are you looking for some particular challenges? How do you see the biomarket? Is high reliability one target? Tell us.
Yeah. So right now you can give us applications, and you can give us different kind of instructions for these applications to test, because we have already tested a quite variety of different applications, and we would like to go further to different applications. And also, what we can offer you is the synergy we have with Heidelberg Instruments. So so we are right now making a new product.
Okay, so let's talk about applications. I'm going to come to you. You give me a challenge and I will address it. We have a company that is doing in vivo monitoring in the room. I'm talking about the company RiverD Diagnostics. And the company RiverD Diagnostics is presented by, you know, when you make these meetings live, at the last minute, when you're introducing the person, his connection drops. That's what just happened. So RiverD Diagnostic is not here, unfortunately. Maybe they will join a bit later. Before we give the floor to the presentation that you all are waiting for, the presentation for LuxExcel, I want to understand a bit from the end user side what other challenges we have in the room. Guido Groot, goedemiddag. Thank you very much for joining. It's fantastic to have you in the room. I love what you're doing. I want to introduce you properly. To introduce you properly, I want to introduce two people who really told me, I want to be here because LuxExcel is here. So the first person that I want to introduce is the CEO of a company in the AR/VR segment, Ralph Knoll. Good afternoon. Beautiful, beautiful background, the one that you have, Ralph. Tell us why you were so excited about having LuxExcel in the room and what kind of preliminary question do you have for them?
Yeah, sure. Well, if it's a preliminary question, first of all, guten Mittag, Guido Groot. What we do is we produce eyewear for the AR industry. It looks like this. This is the first prototype. So it has an outer glass and it has a LCD shutter element inside, and we sandwich these both components. And my first question would be, how many minutes would it take for you to print a lens, and how much will it cost?
Guido, don't answer that question yet. We are going to answer it after your presentation, but this is the first one.
Because I'm asking this question because we are doing this sandwiching thing. We are buying simply Trivex or polycarbonate from the usual suspects like Alcom, Hoya, OptiSwiss, etc. And then we add an LCD, and the lens cost is just €6, roughly speaking. And then we add a shutter, which is maybe €10. So we end up with €16 only per glass, and we have a fully fledged anti-glare system for the end user. And therefore, it's very interesting to see how the competitive landscape is developing in the future. And therefore this question.
I'm going to come back to you, of course, Ralph, with the right answer. Before that, Guido, I'm so happy that you're here. There is somebody else who is very excited about this. We have Harald Pierre from the company Xenogent. Harald, good afternoon.
Good afternoon, everybody.
Why are you so excited of having LuxExcel in the room?
Yes, I would like to learn about the current status of 3D printed optics, because it's an important tool for prototyping, for testing, maybe for mass manufacturing. I think we will hear about it, and cost, of course, that's important. And also because it's maybe a very useful tool to tackle the issue of light pollution in outdoor lighting, because I think we need a lot more and a lot more precise tools to shape light output in outdoor to avoid sending light to locations where it shouldn't go, especially towards the sky. And I wonder what 3D printed individualized optics can do, or even MicroOptics can help and support in getting better cutoffs, better shaping of light.
We have in the room companies like Renault, companies like Leica, like Schott. We are all really excited. I had the honor and pleasure to introduce a success story in Europe right now, a company that switched their business line towards ophthalmic lenses with a truly belief that ophthalmic can be printed on site, and now they're looking for partnerships to bring additional intelligence all the way to AR/VR. They're already the only producers in the world of customized ophthalmic lenses that can actually do at the same time augmented reality. I had the honor to introduce a person that I know already for many years, Goedemiddag, Guido Groot. The floor and the attention of everyone, I'm so excited to say this, goes to LuxExcel.
Thanks, Jose. It's a pleasure talking to you again. We've known each other for years. So
I have prepared a few slides that will answer some of your questions.
The first time I went to see you was like a decade ago. I saw the laboratories, the printer there in Ghost. Things have moved so much and so fast in the last years. I love when great things happen to great people. The floor is yours.
Okay, thank you, Jose. So maybe for people who do not know us, we are a Dutch company, and we have developed over many years the technology to 3D print lenses. And as you might know, we started off by printing all types of different lenses. And over the years, we've really focused on ophthalmic lenses. And why ophthalmic lenses? Well, the main reason is it's a huge market, right? 3 out of 4 people need to wear prescription. And you can see it in all the participants here. It's about 3 out of 4 people need prescription. And secondly, all of these lenses are different, which is of course great for 3D printing, because that's what we do, right? We can make volume products individually customized. And so our focus today is, of course, prescription lenses, but we also found that we have something unique to offer to the smart eyewear space, which is what our sweet spot is today. We have partnerships with pretty much every big tech company that is looking at smart glasses. And all of them rely on our technology to make those smart glasses with prescription. And coming to your comment from earlier, Ralph, I'll explain you why it makes sense to use our technology to do that. So the first question everybody asks us, so why do you want to 3D print a lens? Well, there's many reasons, but if you to put them all in buckets, I think there's 2 main reasons. The first one is, with our technology, you can make smart lenses look like, smart glasses, I should say, look like normal glasses. So we all know the smart eyewear space, everybody used to wear helmets. Well, we're not in the helmet business, we're in the eyewear business. So with our technology, you can actually make these smart glasses look like normal glasses because we make them thin, light, with prescription and fully integrated. So that's a major benefit of our technology. And the second point is, it's a lot simpler to 3D print a lens than to use traditional lens manufacturing technologies. I know there's a lot of people here who are very familiar with traditional lens making technologies, but to make traditional eyewear lenses takes about 30+ process steps. That goes from injection molding to CNCing, polishing, blocking, edging. I mean, you can name it. There's so many process steps. It's a very complex process with long supply chains and a lot of inventory. And with our technology, you print the lens and it's ready when it comes out of the printer. So the 2 main reasons to print lenses is you can make thin, light, fully integrated prescription lenses, and you can do it with 1 process step. How do you 3D print a lens? Well, I simplified it here. So basically, we start with a bottle of ink. The machine makes tiny little droplets, very small, in the picoliter range. We deposit them exactly where they're needed, and then we cure them in place. And we don't cure them fully, we partially cure them so that they integrate with the other droplets, so that you get a fully transparent lens that does not require any polishing and is ready to be used once it comes out of the printer. Yeah, in a nutshell, that's what we do. We make very small droplets. So the reason we're so precise is we use very small droplets. The reason we achieve high speed, coming to your point, Ralph, how long does it take? Well, to print a batch of lenses takes about, depending on the prescription and some more variables, but roughly between half an hour and an hour to print a batch of lenses. So it goes very fast for 3D printing. And that is because we massively parallel deposit these droplets. The other thing that's great about the technology, it's because we use droplets, we let them flow. You can imagine that they become perfectly smooth. So we achieve a surface roughness in the 5 nanometer range. So it's very smooth without any polishing, which is a great benefit, not only because it simplifies things, but also because it doesn't damage, for example, a smart device that you integrate into a lens because there's no force applied. And also because we use these droplets and we do this at close room to room temperature. There's also no stress applied to the lens, and so it's a very usable lens straight out of the printer. We are compatible, our technology, our material is compatible with all kind of industry coating processes, but we can even print coatings. We can make, of course, all the usual shapes and many others with our technology because we build the shape as we go. And we have a family of materials that apply to different applications. How do you integrate smart devices? Well, what we do is we print the front with the power, the back with the right optical powers. We can even create air gaps if the application requires an air gap, or we can print straight on the waveguide if that is possible. We can print the mountings for the light engine, and so we can provide a fully integrated device straight out of the printer, ready to be to click the light engine on. Which is really our biggest benefit. Our biggest benefit is that with our technology, you can make a thin, lightweight, small device ready to be used without any stress, with the mounting attached. And what you get from that are, for example, here are examples of waveguides we have integrated. On the left top, you see a waveguide from WaveOptics that we have integrated. You see the waveguide sitting in the middle. You see that we printed the mounting for the projector to click on. This one actually has a prescription of -1 diopters and +1 diopters on the front. And you can see how we create a device, and that you see the bottom right corner, that you can click straight into a frame. And it's a very lightweight. The thinnest, the back side of the waveguide, for example, we can print at 550 microns thickness, which with traditional lens technology, if you glue them together, you will not be able to achieve 50 microns thickness. On the left bottom, you see another waveguide from Lumos, which is a reflective waveguide that we've integrated. You can see how we kept the entry pupil, the entry prism free of any deposits. We can also print all kinds of other shapes, of course, like these micro lenses that you see on the right top. So with our technology, you can really integrate anything you like into a lens, which is, of course, a great benefit for smart eyewear. So our technology, it's really a turnkey solution. It's one printer, materials and software that comes with it to bring together the process. We work, like I mentioned earlier, with all the big tech companies that are looking to make smart glasses. We have customers that produce this in volume with our technology. So it's a proven volume technology. It's certified, which for ophthalmic lenses is, of course, an important aspect. And we can integrate, well, pretty much anything you guys can come up with, but maybe I shouldn't say it in this audience, because I'm sure you guys can come up with something that offers additional challenges. And yeah, as far as we know, we're the only ones able to do it in this way. Like Rolf, like you were saying earlier, you can of course glue together traditionally manufactured lenses. Absolutely, that's possible. But I believe you cannot achieve the same thickness and weight and integration that you can do with our technology. That's in a nutshell what I wanted to tell you guys, and I'll be happy to take your questions.
Guido, from the bottom of my heart, congratulations. Congratulations. This is a success story in Europe, and you have been for many years interacting with many companies to make it happen. Today you have the services, and through very strategic cooperations, you have actually managed to reach some of the markets. Some of these strategic cooperations are actually public. So I don't know if you want to mention some of them. It's a strategic cooperation that you are exchanging to address this huge market, which is ophthalmology.
Well, I cannot disclose the names for our customers. These are the big, let me just say, these are, you're all familiar with the names, and they're all the big tech companies working in smart eyewear. And they're at the same time extremely secretive. And they ask us, your child, in as a security, not to disclose their names, so we cannot disclose the names of our customers. However, on the supply side, we work together with a number of waveguide companies and other companies that work in this space. The only customers, you're right, Jose, the only customer I can disclose is OptiSwiss. Absolutely, sorry, you're absolutely right. And OptiSwiss is, of course, an ophthalmic lab in Switzerland that we work with. And they use our technology to actually help some of our customers with prescription smart lenses.
We have a lot of discussion to do with you in the next 20 minutes, so please be ready. Let me start. There's a company in the room that is in stealth mode, and they asked me to read the question for them. So Guido, what is the maximum resolution you can print at, and can you print blazed gratings, and at what scale?
Okay, that's a very specific question. So we can print very small features. We have an application today for a customer that needs very small, like I say, dots on top of a lens, and they can be in the 20, 30 nanometer range. So that's the smallest we can go and still achieve a good optical quality. We can print all kind of different features, of course, with this technology. Our strength, of course, is to make lenses that are bigger and look like ophthalmic lenses. Our goal is not to make the smallest possible lens. Our goal is really to make ophthalmic prescription lenses and integrate smart devices into them.
I will discuss this with him later on, but I want to understand a bit. You are doing only ophthalmology, or are you considering perhaps to open up a new area of activities?
We can print any lens, well, not any lens. We can print many different types of lenses. And we have customers actually that also want to use our technology, for example, for camera lenses, and we can absolutely do that. We try to be a little bit selective in which things we print, because in our experience, every application has a different challenge, and we try to be very. We see that we believe smart eyewear is going to be a major application of lenses and of photonics, if you like. So therefore, we want to be successful in smart eyewear, but of course, we can print any type of lens. However, like I said, we are not at the level that we can take on 10 different projects. We're not a mega company at this time. So we want to be successful in smart eyewear for now, even though we sometimes take on little side projects.
Before, in the early part of the meeting, we wanted to address a topic we didn't address very well yet, and it's the topic of testing. And in the markets that you are targeting, very often you have to go to high volume production. We have in the room somebody from the company NTS Optel. Frank, are you with us? Frank Ernst?
Yes, I'm here.
Yes, so we just heard that they are very selective on the applications they are targeting because they have to enable high volume production. What do you bring to the table? And also, Guido, what is the activities that you do for the volume testing? So first Frank and then Guido.
Well, we build testers. Let me maybe share my screen.
Yes, please go ahead.
Let me see if I can find it that way.
I like the Epic members always ready to share the screen. This wasn't prepared, Guido. He wasn't expected to talk, and now he's going to share what they do.
Can you see my screen?
Crystal clear. Go to slideshow mode so we can see it even bigger.
Yeah, but I'm maybe loose then that I share the screen.
Okay, go ahead. It's fine.
Yeah, so what we basically do is the meta lenses, DOEs, or anything on a wafer. Yeah, we can basically test. The tester, of course, in details is very complicated. In basic structure, it's actually very simple. So it's an XY stage that basically positions every lens or DOE or whatever on the right position for the laser. This is a very specific designed laser, basically for every specific meta lens. So the wavelength, but also the beam shape, collimated, not collimated, etc., is all adapted to the specific needs of that metastructure. From there, of course, the metastructure makes its pattern. If it's a DOE, of course, multiple beams. We use a projection screen to basically use it as an integrator, make an image of it, and process this image according the quality requirements of the customer. and then you basically get a good or not good product. Of course, it's a little bit more complicated than that, but that's basically what we do. We do this for passive elements like here, but we actually also do it for active elements. For instance, projectors that are in the augmented reality cameras. They also have these number of beams that needs to be tested basically individually. So we also do this for the active elements, and then of course instead of the laser, we have an electrical connection to that active element. So yeah, we basically do a lot of these things. We have I think more than 30 of these machines out, and basically shipping them on a kind of a regular base for a lot of big customers.
And that was great because I want to go now to Guido. And Guido, how is the current status on the volume testing? I know you cannot share everything. I don't expect you to share everything with us, but is there especially a need? You are open to target new applications on doing the volume testing?
Well, as you know, today, there are no real consumer smart glasses on the market today. I mean, everybody's trying, I don't consider the Microsoft HoloLens a consumer product since I don't see anybody here wearing it. So I guess there are still some issues. As you know, a lot of these people are working on introducing these products to market, and we all know the big names. And I expect that towards next year, probably the end of next year and the year after, we'll see the first products introduced, and then the volume manufacturing starts. So we're setting up production lines for a number of these customers. And there will also be, of course, quality checking. For now, we test the quality the same way we test the quality in ophthalmic industry, meaning we check for optical power, we lens map. And currently, there's a number of companies out there that have measurement equipment for that. I assume that at some point in this process, there's going to be a need also to check whether the integrated waveguide still performs as it should. We have not reached that stage yet, but I'm sure there's going to be a moment where we need to set in line with our production lines also waveguide testing, even though that's not necessarily our competence.
All right, Guido, we have no more question in the room from you, and this one you already know is coming from Harald Pierre from Xenogent. Harald, what's on your mind? Harald, Pierre, yes.
Yes, so I was wondering whether you could print on non-planar surfaces as well, and what are the limitations there with respect, for example, aspect ratio, trenches, and so on. Can you feel that? Or?
So first of all, yes, we can print on non-planar surfaces. In the smart iris space today, the most demands we get for planar surfaces, because the waveguides typically tend to be flat. At least quality waveguides tend to be flat. We can print on non-planar surfaces, where, of course, we need to, there's not really a problem in the aspect ratio. Typically, those lenses tend to be curved. We typically do not like to throw the droplets at too big of a distance because it becomes unpredictable. So it depends a little bit on the diameter, of course, of the lens, because that, of course, determines how big the flight of the droplet is. But we can print on normal curved surfaces in regular prescriptions, so that's not an issue in itself. The only thing that often we need to tune a little bit is if you want very sharp points or very sharp trenches, with a sharp in the trench, because of course we use droplets, so we need to tune the process a little bit to achieve the right pointiness, if you like, of the structures. That's something we typically need to work on a little bit.
Guido, there is, of course, one slide that I really need you to see, because in EPIC we have a company who is developing an entire roadmap to add a new technology to the AR/VR market. I'm, of course, talking about Inoptech. This is a clear partnership. The two of you have to work together. Please do it for me. Ralph, please show us the slide and see how we can bring together this beautiful puzzle.
Yeah, thanks a lot, Jose, and congratulations to you, Guido. Well done. I like your technology very much, and maybe in the future we can cooperate in certain areas, maybe not in all areas, because we have also a coverage for 6 diopter and beyond. So we are talking about really steep lenses and curved lenses like curvature 6, which is a requirement from the sports industry and even military, etc. And I know from your colleagues, they told me that it is maybe a little bit difficult to make steeper curves because you're using droplets. So I don't know. Let's see. I would like to share quickly a slide just to show you what we are doing. I already showed these glasses. You see there's a standard glass in front and there's a shutter glass inside, and we stack them. Let me quickly share the screen, then it becomes instantly clear. I put this on full screen. I hope you can see it.
Crystal clear.
This was the initial idea, to use a very much curved sportive glass. This is here from UVEX, famous company. And we thought about how would it be if we implement LCD shutters. And instead of the LCD shutter, it could be also a waveguide for augmented reality. It doesn't matter. So it's in any case a flat device. And our requirement, which were given to us by the sports industry, even by military, was to say, look, we need peripheral vision of more than 60 degrees. So we are talking about a field of view greater than 120 degrees. And here in this SolidWorks diagram, we actually calculated that it is possible to combine the LCD or the augmented reality display, doesn't matter. This is here where the mouse is. It's a flat device. We tilted it a little bit, like 15 degrees, so that we can incorporate this flat thing into a sexy, fashionable, roundish design. And here you can see the outer glass, and that could be any diopter. It could be neutral, like plano, or it could be plus minus 6 diopter. It doesn't matter. And for us, it was extremely important to address the fashion aspect, because we really wanted to have a, as I already said, a roundish, sexy device. And of course, there is a little gap. You can see it here, but this is only a few millimeters, and we can seal it so that there is no dust in between. And this we call a sandwich structure. We can employ even huge batteries, and it's all light tight. Light tight is another big topic, and now this is our latest design. So light tight is another thing to ensure the best visibility, and therefore we decided to have this beautiful curved design. So to put it in the question now, what do you think? What is your first impression? Is that something also you might be interested in?
Well, if I understand correctly, Rolf, your waveguide is flat, correct?
Yes, they're usually delivered flat, and
yes,
also the fastest LCD shutters are usually also flat.
Yeah, so for us, it's no problem integrating them in the lens and print the powers that you need with it. We print optical powers, many different types of optical powers, and we can align the optical center, because in this case, I think you'll have a slightly non-standard optical design, because of course people will be looking not straight through the center of the lens, right? Since you're
we have bespoke mathematics to recalculate the diopter. If you have, for example, 2 diopter, but you shift the lens 5 millimeters to the front, then it's suddenly 1.8 or 1.2 or something. So we recalculate the values. That is correct. But we thought maybe I can put this into a question. Can you AR code your lenses under whatever 10 to the minus 9 bars? And how do you do the anti-scratch, and how do you do the curvature 6? This is maybe where we have different systems. I don't know. I'm just speculating here a little bit. So maybe there are 2 routes here, right?
Well, Okay, let me try answering all your questions in a row here. There's many questions in your statement here. So yes, our lenses can be AR coated. We cannot print the AR coating because of the thickness at the moment. We're working on it, we're not there yet. So AR coating, we use traditional vacuum or sputtering solutions, and thereby we apply AR coating. How do we apply the anti-scratch coating? We can either use traditional industry processes or we can even print it. So we can print the anti-scratch coating. So typically what we do is we print the lens, we print the anti-scratch coating, and all the other tints or filters that you need, we can print those too. And then we send it off to a vacuum AR coated somewhere. Our lenses are very resistant to pressure. I think it's more a question, can the device that you put inside resist the pressure? And of course, our lens protects the device, but I can imagine if the force becomes too big, you might damage the device that's inside. But our material is perfectly resistant to pressure, to force, to all those things. So yeah, I don't see any major issues. And yes, we can print more than +6 diopters.
Oh, interesting.
I want to ask a couple of final questions to you and to the other speakers. But before that, Guido, there is a company that I want you to meet. The company is called Print Optics. We have a company here, Niels Farbach, who is offering already services of 3D printing of MicroOptics in Europe. And I think there could be some room for cooperation to add your technology to these services. Niels, tell us a bit about Print Optics. What do you do?
Hi, thank you, Jose. Yeah, well, actually, one of the first speakers, Martin Hermatschweiler, we're using his machines. So we're just using Nanoscribe machines and offering the whole service behind that. So if you don't want to get into all the parameters that are needed to actually print really high quality, complex micro-optics, then we can do that. We have researched this topic for over 7 years now. And we have extensive expertise, especially in highly complex micro-optics. So on a scale from 10 microns up to 2 millimeters, multi-lens systems, tilted systems, deeply into the freeform optics. I've prepared this one slider. Let me just share my screen.
Please show it. And I want to go to Guido and to the others to see if there is an interest in offering your technology as 3D printing manufacturers as a service to companies who could actually address more customers in the prototyping phase. Niels, show us.
Yeah, can you see my screen already?
Yes, this is PD. Yes, go slideshow mode so we can see it bigger.
So I think you can see it in presentation mode now.
Yes, you have to switch and yes, switch the display and say Heinz-Lungen.
Okay, can you see now?
You're sharing the wrong screen with us. You're sharing the other screen. So you go
I'm
to
sorry.
display
Okay.
settings.
Now I get
there. Yes, very good.
Let me switch the screens.
Display settings to the other one. Very good.
So now you should see it in a
yes.
way. So yeah, what we actually do is we started the optical design, the wave optical simulation if necessary. So we incorporate the advantages and the possibilities of 3D printing optics already in the design, because there is some specs the typical optic designer would never even think of in designing their optics, and we already incorporate that into our design. Then we have the structural design, and there goes a lot into that because we have developed some steps for post-processing, like we can get apertures and mirrors and stuff like that into the systems at as far in the sub-millimeter scale. Or for example, the system you see on the bottom right, that's just not possible to manufacture in any other way. So looking at the previous discussion, I'm also very much team polymer because just the degrees of freedom we have and the little shrinkage, it's just awesome. And yeah, we can offer the whole process from start to finish. We can measure the optics and supply you with, for example, optics directly on chips, on fibers, on just glass substrates, on wafers, all that. So that's what we do. And to answer the typical 2 questions in this round, what we can do for you is we can take your ideas and make real systems out of your ideas. We just need the specs you want to have, and we do all the rest. And what you can do for us, we're actively looking for partners, especially in medical technology and the optical chip communication, fiber communication technologies to develop cool new products and get our technology into your product roadmap in the early stages. And I think we could help each other out in pretty cool ways.
You are already having a successful collaboration with Nanoscribe. I would really like to see there is a potential cooperation with others. But Guido, I want you to discuss this, of course, not in public. We have another company in the room that is the first time they come to an EPIC meeting, and I would like to give them the last word of the meeting. I'm obviously talking about the company that is in the end user side, Bachler. Bryce Turing came as a spectator. He wanted to learn and listen about 3D printed optics. Bryce, we've been talking about 3D printed optics for 2 hours. As an end user in the process industry, what is your take? Maybe you have some questions, suggestions, room for cooperation with any of the participants today.
Good afternoon. Thank you for letting me talk. I was more joining this meeting for curiosity at first. We are mostly interested into the kind of lighting application and freeform optics in lighting applications, and so relatively large optics. And we are not like large volume manufacturing company, so we would like the 3D printing aspect is interesting for us in terms of rapid prototyping or eventually illuminations instead of going to have a tool made for molded optics. And so that's something I was quite interesting to see if there were already technology available for this type of rapid prototyping for illumination application mostly.
Bryce, thank you very much for being here. And it is 5 o'clock, so I want to go to Guido for the final comment. Guido, as you can see, in EPIC, we had the entire supply chain to add further functionality for LuxXL. Illuminate us, tell us what is the next big thing coming in LuxXL?
The next what? The next
big thing. The next grote thing.
Well, for now, what we want to do is we want to help our customers bring smart prescription, smart eyewear to market. And that is what we're focused on very much. And we think smart eyewear is going to change the world. We think everybody who now has a phone in his pocket, thank you, Ralph, we're on the same page. So we think that everybody who has a phone in his pocket soon will be wearing smart glasses, because what's the point of walking around with a phone in your hand if you have a glass in your head? So we think smart eyewear is going to change the world. Exactly. I see everybody agrees with me here. And therefore, we need to add prescription. We need to make them make comfortable, thin, smart, light, and most importantly, fashionable. And that's where we want to help our customers do that. And we know that there's a lot of interest from all the big tech companies in this space. And we know that pretty much every big tech company has this vision. And so look at, for example, Meta, for example, who've changed their name from Facebook to Meta to make clear what their objective is. And they're not the only ones. We think smart eyewear is going to be the biggest change in computing that we have seen in the past, since the internet came along, probably, I should say. And so therefore, we want to be a part of it. We're going to help our customers do that. And that's going to be a major thing. And it will change the photonics industry.
We started the meeting at 3 o'clock. We finished at 5 o'clock. We start and finish on time. We started with MicroOptics. We finished with large optics. What a fantastic couple of hours. I hope you had as much fun and also as much lead generation as I did. Until the next time, thank you very much. This was Jose Pozo on behalf of the European Photonic Industry Consortium. And that concludes the public part of today's meeting. If you are in our Zoom room, our informal private discussion is about to start. I call it virtual drinks with friends. And we all know follow-up is important. But for now, if you are watching on YouTube, that's where we leave you for today. Thanks to the EPIC production crew and our sponsors for making today's event possible. More details about upcoming meetings are on our website. And if you want to get in touch with any of the participants, all you have to do is contact me directly and I will make sure you get introduced. It is all about connections. Thanks for being EPIC.